So as you know, the question given here, so this is a block diagram. Obviously, it is a unity negative feedback. So it is a unity h of s is equal to 1. So it's a negative sign here, so negative feedback. The open loop transfer function is 20 divided by s plus 1 into s plus 5. And r of s is given here, c of s is given here. So we need to find out the characteristic equations, omega n, zeta, omega d, Tp, and maximum peak overshoot. Here omega n is the natural frequency of oscillation, omega d is the damping frequency. Okay, so both are in radian per second. Zeta is the damping ratio having no unit, Tp peak time of unit second, and MP maximum peak overshoot, that is the maximum amplitude. Third, I need to find out time. Okay, time for fast overshoot. So how much time the system need, or how much time the system is taken to make the fast overshoot. Then after we need to find out the time period of oscillation. Okay, and we need to find out also the number of cycle the system completed before reaching to steady state. Okay, so steady state here I consider 2% error. Okay, so a very precise system. And what I try to say is, in this problem you will learn many more concepts, so do not skip the video, so you may miss some important concept. Okay, let's first try to solve the transfer function. Okay, so let's go to the solution and try to find out the transfer function. Okay, so what will the transfer function? Transfer function is nothing but g of s divided by 1 plus g of s into h of s. Okay, so when you solve this thing, here g of s is this value and h of s is 1 with negative feedback, so I have given a positive sign here. So you will find that is this transfer function is nothing but 20 divided by s square plus 6s plus 25. Okay, this is the transfer function what you got. But the thing is, whenever you try to solve any second order system, we know that the system equation will be in the form of omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay, so this is a standard equation. If I equate this equation with this equation, so it will be like 20 divided by s square plus 6s plus 25. Okay, by looking into this equation, we found that the numerator is omega n square and the extreme last value also is omega n square. The constant is omega n square. Essentially, these two values should be same in equation. But if you look to this equation or this equation, you can see this is 20 and this is 25. That means this is not possible to solve. Am I right? No, this can be solved. So whenever you find any equation in this form, do not bother about the numerator. Take this numerator as the same value. How to convert it? You just multiply and divide by 25. So you will get this equation. How to do that? 25 divided by 25 into 20 divided by s square plus 6s plus 25. If I rearrange this, I reach with 20 divided by 25 into 25 divided by s square plus 6s plus 25. So this is the equation I need. Numerator should be the same value with respect to the constant. Yes, are you getting this equation? Okay. So once we get this equation and we equate with these two, this standard equation and this equation, so it is very clear that this is omega n square. So we can write the omega n square is nothing but 25, and the omega n is under root 25 is equal to plus minus 5. But the algebra will give the under root of any value will be plus minus 5, but here we consider a frequency. Frequency never be negative. So omega n is equal to 5 radian per second. So I got this equation omega n. Okay. So before I actually forgot to solve this characteristic equation. What is the characteristic equation? Characteristic equation is the denominator of the transfer function when equate to 0. So what is that characteristic equation? So now my equation is this, not this. So it will be 20 divided by 25 into 25 divided by s square plus 2, plus 6s plus 25. If I equate the denominator to 0, so either this 0 or this 0, but this is a constant, this cannot be 0, so remaining this term will be 0. So the characteristic equation becomes s square plus 6s plus 25 is equal to 0. This is nothing but the characteristic equation. Clear? So I have found this. I have found omega n also. So the standard equation is nothing but the omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay. So by comparing this, the middle term, okay, what I get? 2 zeta omega n is equal to 6. So this s and this s cancel out. So 2 zeta omega n is equal to 6. That means the zeta, okay, try to make it clear. So this zeta is equal to 6 by 2 omega n, which is nothing but 6 divided by 2 into 5, that is 6 divided by 10, so 0.6. Okay. So how to confirm whether my zeta is right or wrong? See, this is a under damped system. So if they ask for all those things, okay, these things, that means it must be a under damped system. So the response will be somewhat look like this. Okay. In that case, the zeta value will be in fraction, that is in between 0 to 1. Okay. So it is confirmed that this is my right answer. Okay. So we have to find out the omega d. Omega d is the damping frequency. The formula for omega d is omega n under root 1 minus zeta square. So we can write 5 under root 1 minus 0.6 the whole square, and after solving we found the omega d is equal to 4 radian per second. Okay. So previously we found out omega n is 5 radian per second, and we found here omega d is 4 radian per second. Always remember omega n should be greater than omega d. This is very important concept. And if you do not able to understand this, try to compare this thing with this, so that, or you can draw a simple frequency here with same amplitude, and this is omega n, this is omega d. So you just compare these two, and you can understand why this omega n is greater than omega d. So we have found out this omega d. Now Tp, what is Tp? Tp is nothing but the peak time, or can write tau p. Okay, so the Tp formula will be pi divided by omega d, or we can write pi divided by, in place of omega d, I can write omega n under root 1 minus zeta square. So simply I can write 3.141 divided by omega d value will be 4. This will come around 0.786. Okay, 0.786. This is time, so the unit of this will be second. Clear? So I have got this thing also, the TP I have completed. Let me find out the maximum peak overshoot, or MP. So the formula for MP is nothing but the maximum peak overshoot. It will be somewhat like e to the power zeta pi divided by under root 1 minus zeta square. So the value of zeta will be 0.6, the value of pi will be 3.141. Remember, the pi will be in radian, not in degree. So after applying this value, if you equate or try to solve, we will get with the MP will be equal to 9.47 percentage. So multiply this with 100, so we'll get 9.47%. So last class I may have some mistake, I didn't remember, so just try to re-verify. So let's say this is the plot what we actually get, and okay, so this is the desired value, this is 1, this is desired value, I mean steady state value. So the maximum peak overshoot is this. What we find, the MP formula will be this. Okay, this, okay, this value, in between this value. So actually what obviously the maximum peak overshoot is this much, but the formula for MP will get with this value only. So if they ask what is the maximum value of the peak from the bottom or from 0, then you have to add this with 1 or the steady state value. So total value or total MP from 0 is equal to MP plus steady state value. This steady state value. Here I am taking 1. The value of steady state may not be 1. This is different for different problem or different circuit. So that you consider this thing. But you never ask this kind of thing. So they just ask what is the maximum peak overshoot. That means the maximum peak with respect to steady state value, which is just simply this value. Okay, last class in the simulation I also found out, in the last video we have seen the MP will be somewhat around 9 point something percent. So you can see that if this is 100 of 9 will be this much. Okay, 9% of this value will be this much. Okay, so this is the maximum peak overshoot. So we have finished with this one. And the time for fast overshoot, what is that? So this is my first overshoot, this is my second overshoot, this is my third overshoot. But here n is equal to 1, here n is equal to 3, here n is equal to 5. This is my first undershoot, so n is equal to 2. This is my second undershoot, so n is equal to 4. So the odd number indicate the overshoot and the even number indicate the undershoot. So if they ask what is the time for the first overshoot, so obviously time starts from here, that is from 0. First overshoot will be here, so this time they ask. Okay, or the time for the first undershoot or first overshoot, we need to find out the time between these two value. So let me rectify the question. The question is the time for first undershoot. Okay, this is not overshoot, this is undershoot. Okay, anyway, if they ask for time for first overshoot, this time this is nothing but tau p. Okay, so this already we have found out 0.7 something some value. Okay, and now they ask time for first undershoot. So this value up to this, starting from 0 up to this. So what is the formula? Formula for fast overshoot or formula for overshoot and undershoot is equal to pi by omega d. Okay, pi divided by omega d. But what you need to do, you multiply n over here. So overshoot or undershoot time formula now changes to n pi by omega 2, omega d. Okay, so if they ask what is the time taken for fast overshoot, you replace n by 1. If they ask what is the time for second overshoot, this is second overshoot, so replace n by 3, not by 2. Okay, this is the concept you need to remember. Okay, so what is the formula? N pi by omega d. This is the overshoot or undershoot formula. Remember all the things. So replace this n value with appropriate value. So if here they ask time for fast undershoot, this is the fast undershoot. So here n value is 2. Do not confuse with fast and n is equal to 2. So if you recall the graph, then you can understand easily. Clear? So if you replace this n by 2, pi by 3.141 and omega d will be 4 radian per second, the time for fast undershoot will be 1.57 second. 1.57 second. So this is the third question. Okay. Okay, let me try to solve the next question, that is time period of oscillation. So if you try to compare these two, you will reach with one solution that, let's say, uh, instead of under dam system, so just try to draw a simple system. Okay, with same amplitude. Okay, and it starts from 0. Now can you say, or can you find out what is the time period? Time period, if you take this wave from here to here, I mean the time taken for complete one cycle is called time period. Okay, and this is either from any 0 to 0 or from peak to peak. If you take peak to peak, or I mean up to from here to here, or from nip to nip, if you extend this from here to here. So there is no hard and fast rule from where you can calculate the time period, but it should be with same distance. Okay, in previous question we found out time period for fast undershoot, I mean this time. If I know this time, some from this down peak of this down peak, यहाँ पे अगर, so the next previous wave down peak will be somewhere here. So this time, obviously this is a under dam system we have studying, under dam system. So like this, so we can take this as my time period. Okay, TP, and obviously we know that the time period, okay, T is equal to 1 by F. That means the reciprocal of frequency, and we also know the frequency, or you can write the frequency in this form, 2 pi F is equal to omega d. Here we considering omega d, a damping frequency, as because my damping system will be under damped system, not a perfectly damped system. Okay, so the peak and amplitude may vary. That is why we are considering omega d. So we know that F is equal to omega d by 2 pi, and time period tau is equal to 1 by F is equal to 2 pi by omega d. Okay, this formula we have seen for time period of first undershoot. The same value, 1 point some value we have got previously, that is 1.57. Okay, we got 1.57 second. So we complete the fourth one. Then they ask number of cycle completed before steady state. तो यहाँ पे अगर हम 2%, so अगर मैं so if I try to draw a diagram to make you understand, so let's say this will be my underdamped system with a error of just 2%. Okay, this error value is 2%. That means system is very precise. So you can, from this diagram you can see that this is a cycle, this is another cycle, and this is another cycle. So 3 cycle. So the question try to ask how many cycle the system has to complete before reaching the steady state value. Okay, so we know that if I found this time period, that is TS, settling time, if I know the settling time and if I know the time period TP, okay, so I can find the how many time period can be happen in one settling time, so that the number of cycle can be equal to TS divided by T period, time period of a single wave. Okay, so if I try to solve using the formula, so what is the type period of oscillation for TSS for 2% error will be 4 divided by zeta omega n. Substituting this value, we find TSS is equal to, okay, and we know this is settling time, and time period of oscillation TP will be 2 pi by omega d. So if you substitute the value and find with is 0.848 cycle. That means to solve this, to reach the steady state with this system, it actually never take more than a cycle also. So 84% of a cycle. So if you want to simulate, you can simulate and find out whether the solution is right or wrong. So this is all about the system, all about the problem. So we have learned some concept here. We have learned if the numerator is not omega n square, then how to convert it. Then we have learned how to find out the number of cycles. Then we learn that the time period of second undershoot is equal to the time period of the system. And we also learn about for different value of overshoot and for different value of undershoot what will be the n value. Okay, so for overshoot n will be odd number and for the undershoot n will be even number. So these are all the problem. Try to find out some more problem from the book and solve. If you have any question or doubt, you can ask me in the comment section. I'll try to reply as soon as possible. Here the question says the unit step response of a second order system is 1 minus e to the power minus 5t minus 5 e to the power minus 5t. This is in time domain. Okay, time domain. So always remember, convert a time domain into frequency domain to solve my problem. To solve the problem, the first statement is given that under damped natural frequency is 5 radian per second. So this is the statement to make you confuse. So it was given under damped, then also asking natural frequency. So it is actually omega n. Natural frequency means omega n. So do not confuse what is, if they ask under damped means you try to find out omega d. Okay, this is not the thing. So natural frequency means it is omega n. So the damping factor or damping ratio is 1, which is nothing but the zeta. Then what is the impulse response? So this is a step response it given. Then what is the impulse response is this value. So we know that the derivative, okay, derivative, or you can write in this way, derivative of step is equal to impulse. So just that in this case, if the derivative of step is impulse, similarly you can write derivative of step response equal to impulse response. So you take the derivative of this value, you can get to this value. So let me check it out. So what is the Laplace transform? Laplace transform of this equation is equal to 1 by s minus 1 by s plus 5 minus 5 divided by s plus 5, okay, the whole square. You know that how to do the Laplace transform, and if you try to solve this, you will reach with equation which is nothing but the 25 divided by s into s square plus 10s plus 25. Okay, so you take this s outside, 1 by s into this value. So if they ask what the characteristic equation, then equation denominator 0, either this is 0 or this is 0. So this will be equation. So this cannot be 0. So this is the equation. So characteristic equation is s square plus 10s plus 25. Okay, so this can be equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. This is very clear. Okay, so from this equation we can find out the natural frequency. So here omega n square is equal to 25. Obviously omega n is equal to 5 radian per second. So this statement 1 is correct. Okay, so here 2 zeta omega n s is equal to 10s. So 2 zeta omega n is equal to 10. So zeta is equal to 10 by 2 into omega n, which is 5. So 10 by 10 is equal to 1. So damping factor, damping ratio is 1. The statement 2 is also correct. So to find the impulse response, so just take a derivative d by dt of 1 minus e to the power minus 5t minus 5 e to the power minus 5t. So if you take the derivative, the derivative of 1 is equal to 0. So derivative of this will be minus of minus plus 5 e to the power minus 5t. So here 5 into 5, 25 plus 25 e to the power minus 5t, and for this one we'll get minus 5 e to the power minus 5t. So these two will get cancel out. So the impulse response is 25 e to the power minus 5t. So this is the value. So option 3 is correct. So in this way you try to solve all the problem, at least try to solve some 10 to 20 problems, so that it is very easy to solve in your semester examinations. Okay, thank you very much. If you like the content, please don't forget to like, share and subscribe to Spark Study channel, so you will get new update. Don't forget to hit the bell icon also. Thank you very much.